Okay, for today, I would explain about combinational circuits, which is the chapter 5 of the digital logic. So we have designed a circuit that implements the Boolean function. So this type of circuit is an example of a combinational logic circuit. We call this as a combinational circuit because it produces specified output almost at the instant when input values are applied. For example, if we have 0, 0, 1, x is 0, y is 0, and then z is 1, so it's automatically produce the values, okay, based on these functions that we apply. However, in a later section, we will explore circuits where this is not the case. So, continuing about the combinational circuits, one of the simplest example is the half adder, which finds the sum of 2-bit. So, as we see, the sum can be found using the XOR operation and the carry using the AND operation. Half adder, okay, usually is used on the first bit of the operation. For example, if we have 4 digits of 0, 1, 1, 0, and then 0, 1, 0, 1, like this. Okay, so this is the first digit. Okay, so this is the first digit that we require to use the circuit to add. So this is x, this is y. Okay, so the output will be 2 because there's a possibility that there is a carry out. Okay, so here will become a sum. This will become a sum, and then when there is a carry, okay, so means that there is some output there. Okay, so the truth table, okay, would be applied based on the operation of adder. So 0 plus 0 is 0, carry 0, 0 plus 1 is 1, sum is 1, and then carry is 0. Okay, and then 1 plus 0 is 1, carry is 0, and then 1 plus 1, okay, so 1 plus 1 is basically 0, and then carry out 1. Okay, so that's why the sum is 0, and then the carry is 1. Okay, and then the logic circuit, okay, can be derived or can be drawn, okay, using the same input. Okay, since they are using the same input xy. Okay, and then for the sum, okay, we can represent using x bar y and then x y bar. So it also is the same for XOR. Okay, for the XOR. So the logic circuit that we use is x XOR y. Okay, for the sum. And then for the carry, okay, so basically this is xy. Okay, so only xy will produce the output. So we just tap on the xy and then AND it together. So you will get another output, which is the carry. Now, for another example is a full adder. We can change from half adder into a full adder, okay, because of sometimes the input, okay, 0, 1, 1, 1, like this. Okay, so full adder is after the first bit. So here, here, here. Okay, so there is some possibility there's a carry in, so to become the input. Okay, carry in will become the input. So that's why it require 3 input. One is the in x and y. For the output, it will become a sum and then carry out. Okay, so the input is xy, carry in, and then sum, carry out. Okay, the combination is the same, 0, 0, 0 until 1, 1, 1. And then for the output, we have a sum and carry out. So we can add it together, okay, and then derive the SOP expression for the sum and also the carry out. Okay, simplify it using Boolean algebra or using the K-map. And then after that, we can draw the circuit. Okay, so the direction or the circuit can be a little bit different, but if it's give the same truth table, then it is correct. Right. Another combination circuit is the decoders. The decoders are another important type of combinational circuit. Among other things, they are useful in selecting a memory location according to binary value placed on the address lines of a memory bus. So, when they want to try to find a file, okay, they need some address. So, this address must be decoded. Okay, so they use the decoders to decode the input of that address. Decoders use n input and then 2 power n output. Okay, n input with 2 power of n output. So this 2 power of n output is the location or the address. Okay, in the system bus. These decoders also can be applied in CPU control, which is an advanced topic that will not be covered in this degree subject. Okay, the figure here shows the block diagram for a decoder. Okay, one of the example is that we have 2 input and then 4 output decoder. So we can call it as 2 to 4 decoder. Okay, so for the decoder, okay, they have several combinations. So if x is equal to 0 and then y is equal to 1, which output line is enabled? Okay, so we have x bar and then y. So here we can expect that it will go out to here, x bar y. So y, it will go to here, not. From not, we can go to this line and then go to this line. And then for y, they will go here, going to this line, and then going to this line. So as we can see, only this gate is completed, okay, is complete, which is connected. So that's why it will go out, okay, to this output line, okay, x bar y. Right, for the multiplexer, it's the opposite of the decoder, whereby it selects a single output from several input. So let's say we have a several line of input, and then we need to choose one of these input to take out to bring to another destination. Okay, so it's like a pipeline. Okay, you want to select which chemical that you want to go to release, okay, and go out as the output. So this is what multiplexer do. So the particular input is chosen from for output is determined by the value of the multiplexer control line. So to be able to select among an inputs, okay, how many control lines is needed? So let's say for this control line, they use log n base 2. Okay, example, we have for input. So log 4 base 2 is equivalent to 2. Okay, equivalent to 2 means that for 4 input, it require 2 control line. Okay, so go to be selected going out as an output. For example, this is a 4-to-1 multiplexer. So it means that for 4 input, it requires to select input. Okay, to select input. Okay, if S0 is equal to 1, S1 is equal to 0. So means that S0, S1 bar. Okay, so S0 means it goes to the north. Okay, means that going to this line, going to this line. Okay, next is oh sorry, not this one. Okay, so it should go S0 to this line and then to this line. And then S1 bar. Bar means go to the north and then to this line and then to this line. Okay, so we know that input, okay, is waiting to be sent out. So there's a line here and there's a line here. Then I1 is here and I0 is here. Okay, so look at each gate. This one is incomplete, this one is incomplete, this one is complete. So the one that is completed will be ended and then sent out as the output. Okay, so in this case, the I here would be the value that will be the output for this multiplexer. Okay, so that is several example of combinational logic. Okay, now I will continue with the next category of the circuit, which we call as the sequential circuits. As the name implies, sequential logic circuits require a means by which events can be sequenced. Okay, it's like we want to create a sequence of numbers, so we want to get the result. Okay, so we want to get the result or maintain the result. Okay, so that's mean we require some events. Okay, events that need to be sequenced. So state changes are controlled by clock. So a clock is a special circuit that sends electrical pulses through a circuit. So in this case, our CPU line, okay, our CPU hertz is what controls the timing or the cycle of that clock. The clock produces electrical waveforms such as the one shown below. They have a rising edge and then the falling edge. Okay, this is a high and then this is a low. Okay, so this clock produce electrical waveform like a cycle, So one cycle and then two cycle, three cycle, four cycle, like that. Okay, state changes occur in sequential circuits only when the clock ticks. So circuit that change state, okay, on the rising edge or falling edge of the clock pulse are called edge triggered. Level triggered circuits change state when the clock voltage reaches its highest or lowest level. So to retain the state values, sequential circuits rely on feedback. So this is how or the characteristic of the memory in RAM. So they use a feedback which occur when an output is looped back to the input. A simple example of this concept can be seen on this figure where if Q is 0, it will be feedback again to become an input. Okay, so that's why 0 will always be 0. Okay, but if Q is 1 at one clock stage, so it will be feedback and then it will always be 1. Okay, because of this characteristic of feedback. Okay, so to retain the state values, sequential circuits rely on feedback where an output is looped back to the input. Example of feedback is the most basic sequential logic components, the SR flip-flop, where SR stands for set or reset. As you can see here, okay, the Q value or the output will be feedback to R, and Q bar will be feedback to R, and then Q would be feedback together with the S, okay, with the NOR gate, okay, to the NOR gate. Okay, C here is referring to the clock. Okay, so when the clock change, and then the state will change. Right, so the behavior of an SR flip-flop is described by a characteristic table. Okay, this is a characteristic table. So this will be what is the expected value when something happens. So QT means the value of the output at time t. The t plus 1, QT plus 1 is the value of Q after the next clock pulse. The characteristic of SR flip-flop is that when S is 0, R is 0, they refer to the QT, means no change. So when it says no change, means that it retains, okay, the current value. If the S is 0, R is 1, means that reset. So it will be reset to 0. Okay, so QT plus 1 will become 0. If the set is 1, reset is 0. So it will be set to 1. And then if S is equal to R, which is equal to 1, it will become unstable. Okay, so that's why it says undefined. Okay, we can see on this truth table here, the SR flip-flop actually has 3 input. One is the which consists of S, R, and the QT, which is the present state. Okay, or we can say its current output. Thus, we can construct a truth table for this circuit. Okay, the usual is the same, but for the next state here, QT plus 1 is referring to the characteristic table on the previous slide. So let's say S is equal to R, which is equal to 0, both is 0. So it would refer to the current state, to the present state. So the next state will become 0. And then if QT is 1, it will become 1. Okay, next, S is 0, R is 1. So means that it will need to be reset regardless of the value of QT. So the next state will become 0 and 0 because of the reset here. Okay, and then for 1, 1 means that we need to set to 1. Okay, set to 1 means QT plus 1 will be set to 1 and 1. Whereas for the S is equal to 1, R is equal to 1, this will become undefined, which is unstable. Okay, so notice that SR flip-flop is unstable. So it can be modified. SR flip-flop can be modified to provide a stable state when both inputs are 1. So this modified flip-flop is what we call as JK flip-flop. The JK flip-flop characteristic table is that the first 3 conditions, 0, 0, 0, 1, and 1, 0, follow the same state of SR. Okay, except that on the fourth state, J is 1, K is 1, it would follow the Q bar T. Okay, Q bar T. Okay, this is what it looks like for another modification of the SR flip-flop, which they call as the D flip-flop. The D flip-flop is the fundamental circuit of computer memory. It's usually used in the static RAM. Okay, static RAM on the cache. Okay, or it's because of it's the basic circuit of a computer memory. The characteristic table of the D flip-flop is that if the D is 0, then QT plus 1 is 0. And then if D is 1, QT plus 1 is 1. It means that it retains the previous value. Okay, it retains the previous value. So that's why D flip-flop becomes the memory cell. Okay, that's all for the chapter 4 and chapter 5. So we can see that computers are implementations of Boolean logic, where it can be completely described using the truth table. So from the truth table, we can derive the logic gates. Logic gates are small circuits that implement the Boolean operators. The basic gate that we learned so far is AND, OR, and NOT. XOR is very useful in parity checkers and adders, whereas the universal gates are NOR and NONE is much more preferable because it's inexpensive and can represent other basic gates. So computer circuits consist of combinational logic circuit and sequential logic circuit. Combinational circuit produce outputs almost immediately when the input change. Sequential circuit requires clock to control their changes of state. So the basic sequential circuit in it is the flip-flop. The behaviors of the SR, JK, and D flip-flops are the most important to know. That's all for now. Thank you.